So let's take a look at the different types of chillers. Okay, the centrifugal is the most common type of chillers. That's what we saw, okay, in the central plants when we toured. Okay, functions as a vapor compression cycle, and this is your compressor, and it usually has an external drive motor. So when you look at this particular unit, accessibility all the way around it is going to be key. Can I access the top of the motor? Do I have a place to set the motor when I do remove it? Because for me to remove the vanes, okay, in this compressor, I have to tear the entire housing apart. So can I get an A-frame? Or do I have my piping that's right over the top of that where I can't? And these units, they're not on wheels, so it's not something you can just push out, maintain, and push back in, even though that's a thought. Thinking about it, right? Okay. And again, it has a hermetic external motor drive. Okay. In this case here, this one's an open drive, so you actually see the coupling that actually couples right through the compressor. So for maintainability, if my motor has to be rewound or it has to be rebuilt or if it fails, I don't have to take the entire chiller apart. All I got to do is disconnect the motor and connect the replacement motor in its place and put the machinery back in service. Okay. Direct drive, typically low or gear driven, which are high pressure machines, so depending on the application. And then the breakdown comes down in regards to the type of refrigerant. So in this particular one, the 123 is typically for low RPM. But look at the 134A. That means that piece of equipment is turning 19,000 RPM. So you imagine what the wear and tear of all the components, the bearings, the bushings, okay, your shafts, okay. In this case here, if you have shims, okay, in that particular piece of equipment, bearing races and so on. So this is why maintenance now becomes so critical. If you're using this piece of machinery, 724, 365, the amount of wear and tear on that piece of equipment now becomes critical. Because again, you go back, I want to maximize the life of the chiller, typically 20 years. Okay, I want to get as many years as I can, because the end result is, if I could extend by 5 years and not replace the chiller, say for $500,000, I can now invest that $500,000, right, and draw some interest. But if I'm only getting life, that means I can guarantee I'm going to have to replace it at 20. Okay, so again, this is probably the most common type of chiller, and this is a real quick breakaway. You've got your water tubes that we looked at. They were actually punching out the condenser tubes on this side when we were looking at them. So on the water side, basically is what you do is once you heat up the refrigerant coming in from your building, your air handlers per se, that water is cooled, but the byproduct is heat. So now what happens is the condenser water removes the heat from the refrigerant, boils off, compressor compresses it back down to a liquid state, starts a cycle all over again. But on the back end, that heated water now goes to your cooling tower to be cooled and start to process all over again. So complex, even though it's a simple, pretty complex in regards to moving parts and of course reliability and requirements. Absorption chiller is a little bit different. Those run on steam. They run on heat, some sort of heat energy. Okay, it's not so much motor driven, but in this particular one here is going to be run on heat. So this almost reminds me of the boilers. You got supply and return, and you got your condensate. But here's your water tube. Okay, this is going to be your water vessel where you have your refrigerant. What I'm doing is I'm turning mechanisms. I'm turning a turbine from within that. And what I'm doing is compressing right to refrigerant from vapor back down to a liquid state. So typically they're heat-driven machines. Heat sources, any multitudes, hot water, steam, okay? Heat transfer properties are usually lithium bromide, okay, ammonia, and some sort of water refrigerant, okay, so a saturation. Single or two-stage operating cycles typically. Okay. Single-stage units use concentrators or condenser sections to initiate the heat transfer, okay, be going from one turbine to the other, okay, for operations. And then typically the two-stage, okay, have operating tendencies just like the different type of refrigerants at a higher pressure. So these are great. If I have a heat source like what we had in the combined heat, if I run it to run a chiller and I didn't want to tie into the electrical grid, I can actually use an absorption chiller and using that waste byproduct, that waste heat, to run my turbines or my compressor, if you will, on this particular. Okay. It's kind of funny. I use heat to produce chill water. So that's the two different components on a single piece of equipment. Okay? And the last one is a rotor screw, okay, machine. And these are great for compact areas. If I have an area where I don't have a lot of space. In some cases, if I have a smaller building where maybe I need a 300 or 400 ton cooling load, I don't need a large chiller. So I can install a rotary screw chiller, okay, and it has its advantages, okay. And one is designed for liquid cooling, okay, and typically they're going to be oil injected. In some cases, they'll be non-oil injected, different types of units and applications, okay. Positive displacement compressors. So basically what I'm doing is, one, I'm using screw mechanisms for the refrigerant and as well as the chilled water, okay, for the cycling, okay. So two different types. But again, I'll go back to maintenance, having accessibility to the panels, to the controls. So I don't want to build a wall right along this side, or I don't want to put additional pumps I got to walk over. So accessibility to these pieces of equipment is going to be key. Okay, and then cooling towers. We've covered this for most of the semester. Big item on this one here. It's a heat rejection device, big evaporative cooler, if you will. Okay, and it uses air for that particular case for the cooling process. So water vapor values are typically measured by the air wet bulb temperatures. Okay, typical measuring device per ASHRAE. Lower design approaches temperatures to more expensive operating costs. So if I need a lower cooling tower water temperatures, in some cases I may only get 80, maybe to 75 degree water coming out of my cooling tower. If I require to run, say, 72 or maybe even 70 degree water at my sump, and this is in the middle of July, one is going to be more costly because I have a fan I have to operate, controls that I have to operate, and of course the water treatment processes. So typically the higher temperatures are going to be the less cost in regards to cooling tower operation. Okay, so say for instance a 5 degree delta, okay, can cost up to 60% more than a 10 degree delta in some of the design towers. So again, depending on the application. Now all this will be designed. Your mechanical engineering consultant firm will design and size the cooling towers. Our job in regards to maintaining them is, again, accessibility. Can I get to the sumps? Can I get to the media? Do I have sand filters? Do I have water pressure? We saw a pump that they were using in the combined heat facility. Is my piping labeled? Okay. Are my strainers easy to get to? Okay, or do I have to stand on a ladder to get to the strainers? Okay, so those are some considerations to think about. In natural draft towers, typically you'll see these in nuclear generation facilities. They use a chimney effect. They really don't have a motor or a fan. They use a natural draft. Heat rises to the top, so they have a natural draft effect. But these are large cooling towers, typically made out of concrete. Okay. Force-induced draft towers use mechanical fans. Instead of using the natural ventilation, heat rising, some of these will use a fan. Okay? One thing I always thought on fans is, could you produce energy from a fan on a cooling tower? Because if you're blowing air up, right, and you see the plume coming up, could I put a little turbine up there and maybe generate some power out of that? Those particular cases. These are, remember I told you I got a long drive to and from work? And I think about all these things. I got nothing else to think about, especially if I don't like the radio station. Right? So you all kinds of goofy thoughts and so on. Okay. So the different types, the field directed, these are basically the built in place. Okay. So typically going to be concrete towers. Okay. Package units. Sometimes you see them in the freeway. So once you see them in the freeway, it says, I know what that is. That's a cooling tower. And then probably whoever you're driving with says, who cares? So, but I know what that is because I learned that in class, right? Typically package units, you set them with a crane, it's plug and play, connect the power, connect the piping, and you're ready to go, okay? Probably do some calibrations in regards to water treatment. Forced draft or induced draft, they need a fan. Natural fan, you use a chimney effect, and their heat rejection devices, okay, overall. And water treatment, these are different types of components, dealkalizers, deaerators, okay? Reverse osmosis units, filtration units. So what I'm doing is I'm taking my condensate water my reject water, and I'm going to filter that. The cleaner the water, the better. One is they prevent fouling from within the chiller tubes. Okay? And the fouling can be contaminants, such as sediments. You can have minerals and calciums. Some cases, you're going to have different types of calciums and minerals from within the water that can provide that suspended solids. Magnesiums is another source. I have reclamators on my towers in Scottsdale. Gosh, and I'm going about 18 years, almost 20 years that I've had these units. And, you know, if I think about the amount of millions of gallons of water that I've saved from reject water, because again, once you get to a certain suspended solid from within your tower, then what you need to start now is start introducing fresh water, city water, into your basins, into your sumps to make that water up. So you'll reject a certain amount. It's like, you know, basically, you know, dumping it out on the street, but it goes into a drain, okay, or backwashing your pool, sand filter. So in those particular cases, instead of letting that water go into the sewer, the reverse osmosis units basically take that reject water, they filtrate it, and then they reinsert that reclaimed water back into your sump. Some cases a lot cleaner than what the city's given you. Okay? But it does extract chemicals as well as suspended solids on it. But it serves its purpose. Okay? Electrodialysis reversal units, these are basically electrically operated water treatment systems. There's no chemicals. It's all set by UV and also through electrical properties, such as taking the current, right, and using that to really coagulate the different types of minerals and then filter those out. Okay? And then your dematerializers, such as sand filters. So you'll always have sand filters within a cooling tower platform, because that's going to really collect a lot of your large deposits, okay, in regards to your minerals and magnesiums and so on. Okay. So chemical water treatment, again, prior device, primarily designed and applied to remove common makeup water contaminants. Every city provides water to you, and there's a certain code requirement, okay, by the EPA, and what you're going to provide water qualities. So there's a certain amount of salts, and there's a certain amount of minerals. You name it in regards to what makes up that water. So in these particular cases here, calcium and magnesium are going to be my contaminants. Now, for our bodies, they absorb those, and part of it's what keeps us going, okay, as human beings. But when you talk about metals, those are the items that attack the metals themselves. So it's not only the piping, but it's also the valves, and also different types of metals, such as cast iron and copper. Okay, in some cases, steels and aluminums. Okay, chemical analysis of the makeup water typically determines the type and quality of the required chemicals. So, depending on water back east on the eastern coast, extremely soft water. Okay, they sometimes pull cycles up to 5 to 6 cycles in their cooling towers. Very minimal chemicals. Here in the southern, southwest states, California, New Mexico, Arizona, heavy in sediment in our groundwater. Okay, and that's where our region is, where we're located. Okay, so for our chemical makeup, it may become a little bit more harsh. But what would I have to worry, though, on my cooling towers back east? You know, again, water is water, regardless if it's soft water or if it's heavy and suspended solids. So, you know, I need to look at different types of properties on my towers back east. In some cases, when it becomes freezing temperatures. So, you know, those are the items that I have to consider. Pipe movement, splitting. Okay, so those are some items that I'm going to have to pay attention to. So again, every region, right, is going to have, I'm going to say, its issues. Chemicals such as phosphates, polymers, and hydrazine allow oxygen or suspended solid, like magnesium, to bind. So they use those additives for that primary reason. They're too fine to go through a filter. They're too fine to go, in some cases, some RO systems. So they use the polymers to really coagulate the suspended solids into larger units so you can filter them through. Like I mentioned, it's a whole science when you talk about water treatment. I was thoroughly impressed when they have their own in-house water treatment technician here at ASU. Okay, and then I'm getting down to the last of my slides. Pumps, condensers, piping, valves, traps, and insulation. Again, part of the infrastructure, part of the building makeup, part of the building systems. Okay, so pumps, you're using that to what? Move a medium, air. You can move water. You can move liquids, gases. Okay, and of course condensers in regards to what you're extracting. some case condensate water, condensation. Piping, valves, traps, and insulation, again, all these are going to require maintenance, okay, maintenance of some sort. Okay. So pumps primarily, centrifugal, rotary, and reciprocating pipes. Now, see that pump here? That's probably the simplest pump we've ever invented, except it takes a lot of horsepower with your arm, right, pumping up and down, okay? So centrifugal pumps are the most common, remember that one, and must have a drive such electric motor, so it has to be some sort of mechanical driven pump. This particular one here is hand driven, so you can do this. When you get tired, you stop pumping, right? Rotary pumps uses positive displacement, very much like the rotary, okay, screw chillers that we looked at earlier. And basically what they do is force fluids between two moving rotors is all. Okay. In some cases you can control the static and also the dispersion of water, so you can modulate that. Reciprocating pumps are also positive displacement. Okay. However, use reciprocating pistons and chambers to move water in that medium. So two different types of applications in regards to pumps. You have inline pumps. You have vertical pumps. You have sump pumps. Okay. You have rotary. I mean, there must be at least 25 to 30 different types of pumps that you can have in any one type of building. Each pump is going to have its own maintenance plan. Each pump is going to have its own expected life use and application for these particular pumps. Okay. And depending on the application, such as petroleum or corrosives. Okay. Condensers, basically heat exchangers designed to remove latent heat from a vaporization intended to convert vapor to a liquid state. So what I'm doing is I'm taking vapor, such as steam, and I'm condensing it back down to a liquid. One, so I can get rid of it. So it doesn't contaminate my insulation or my piping. Okay, in some cases, my building or my systems or my equipment. So two types of condensers. You have your direct and your direct contact and surface. Okay, so two different types of condensers, two different types of applications. The first type of these, direct, mixes liquids and vapors to allow vapor to reject its latent heat. So it's a pass-through, very much like you're going to have a, well, not so much a cooling tower, but a plate and frame. Okay, you're going to have a solid, you're going to have waters with a medium. It's going to extract that particular latent heat from that. Okay? The second type transfers the latent heat energy to a surface to another fluid, typically a lower temperature than a vapor. Okay, so in these particular ones here, I will take a lower temperature, mix it to the surface tubes, if you will, from a higher temperature so I can temper that. But I'm going to use the two. They never mix. There's two different types, but I'm using that surface basically to remove that latent heat from that. Those require maintenance, valves and controls, and of course my tubes to make sure that one, they're not plugged or they're not compromised or leaking. Okay. And piping, believe it or not, piping that you see, process water such as hot water, chill water, domestic water, airlines. All of those are going to require some sort of maintenance. Predictive maintenance primarily is ultrasound, is going to be the instrument of choice. What you're hearing for is frequencies for any leaking valves or air leaks within a compressed airline. Anybody ever imagine how much air leaks from a compressed airline? A lot. Okay, and it just, it breaks down. The fittings break down. The valves break down. So your compressor, you'll notice that it cycles more often than it used to. Okay? Sometimes you can tell that in your air conditioning unit at home. I remember when I first installed it, it used to cycle like every 20 minutes. Now when I'm watching TV and it's cycling, every 5 minutes, that means telling me it's not holding the temperature in the home. Somewhere I've got a leak. Maybe the ductwork, maybe there's a window open. Okay? So piping, various forms, materials, and uses. So what are some piping type of materials? You got cast iron, steel, copper, aluminum. You got your plastics, PVC, CPVCs, okay? You got ABS. So basically it's a medium to what? To transport some sort of liquid, okay? Depending if it's sewer, depending if it's water, okay? Pipe expansion. Look at that, up to 3 inches per 100 linear feet, depending on what the medium's going through the pipe. These pipes where you see on rollers, you kind of think, well, that's kind of cool. They can just roll the pipe back and forth. Well, no, they have it on rollers to what compensate for that pipe expansion. So if you consider 3 inches every 100 feet, imagine if you didn't give yourself play at the end of that 90. and you had it right against a concrete wall. So if it pushes 6 inches for 200 feet, you've got to make sure that you include that in your play. Okay? So, can I get to the strainer or can I get to the valve? Because now once it expands, I can't really get my wrench back into what removed the bolts, okay, in that particular case. So condensate removal, steam piping must be vented to sustain proper temperatures and performance, releasing the excess steam, the excess temperature. So part of that's going to be a steam trap. So the steam traps are going to have to be inspected. Back east, they have a bunch of steam traps. And when they're not functioning properly and they continually vent on a regular basis, that's energy that you're wasting. So in those particular cases, they're going to have regular PMs to check the vent lines. Here, my maintenance is going to be in condensate pans because I have high humidity. It's not so much I'm using steam, but I'm using chill water to extract the high humidity water, if you will, in the air. So my biggest item here is going to be condensate pans to make sure that they're draining properly. Okay. Steam traps remove condensate, cold startup condensate, and evacuates air non-condensables. So in these particular ones here, is that when you start up that hot water system and you bring it up to temperature, these particular units, the condensate and the steam trap is going to have to make sure that they're being, one, they operate properly, okay, and they're being inspected. So typically after you start it up, you will walk the entire circuit and you look at all your drains, you look at all your traps, you look at all your valves and the inside of your air boxes, typically along your coil pans, to make sure that you have no water, primarily hot water or chill water, depending on the application. And of course, insulation just allows for sustained temperatures. Again, energy. What I'm trying to do is maintain that temperature within that pipe, at that temperature for as long as I can, because the boiler that's 1,000 feet down is going to continue to produce hot water. But if I don't have good insulation properties, because it hasn't been maintained, now what I'm going to do is go back to the boiler and then heat it up even more. Now I need a pump, bigger pump, to push that medium down so I can heat the building. Okay? So this is why maintenance becomes so critical in how well the infrastructures operate and how reliable the infrastructure systems are. Okay? So maintenance needs, again, we go back to the very basic, okay, is access and exit routes. So any piece of equipment, consider in the future is how do I remove that? Oh, it's never going to be removed. Well, that's not necessarily true. Okay, it's going to have to be removed at some point, okay, in its life. Okay. Staging equipment, okay, dismantlement and inspections, again, getting back to the infrastructure, making sure that I have access to that particular piece of equipment. The fan coil units, gosh, if I can give you any type of recommendation, put them out in the lobby where you can actually get to them, and not in the middle of the classroom where I got to disrupt a class or stand on tables. So whenever you install those, our return air grills, same thing. Put them next to a door where I can just slip in, replace the filter, put it back in, and then slip right back out. Okay. Labels and identification. You'll be surprised how many times systems are installed and there's no label on and off. So what do you do now? Guess? Let me see. If I turn it this way, it makes a grounding noise. So that must be on. So if I turn it this way, it stops, right? So some of the simple things happen, but that's part of your commissioning. So you'll look at chill water labeling, supply and return, condenser water, domestic water, okay, compressed air, processed gases, and so on. Identifications. Where's the traps? Okay. Where's your domestic water, your main water shutoff lines? Documentation and, of course, identification. O&amp specifications typically built, okay, to those. And then as-builts, another item. For the construction folks in here, as-builts, they're worth their weight in gold, especially to a facility manager, because they're letting me know exactly where that cleanout adds. Once I put the landscape in and I put my pretty rock and my bushes over my cleanouts, I'm never going to find those again. But if I got good, reliable as-builts, okay, that's perfect. Or even better yet, and of course my landscaper, we always get into arguments. Give me a stubble where I can see that cleanout. I don't want to fish around and dig for a shovel 2 feet down. So it says, but Patrick, that's going to look ugly because you're going to see the stub sticking up. That's okay. I'll put some black rocks around it, make it blend, right? But I want to be able to get to that particular cleanout, in this case, fast, convenient, okay, and efficiently, okay? Has anybody ever done any sewer work in your homes? Ever tried to find a cleanout? older homes, my home was built in '68. The clean out was a T. That was my clean out. And my clean out was 4 feet down when I finally found it. So how do you put a snake in a T? Next to impossible. So you put the double sweeps. So you can either go into the home, depending, or you can go back out to the alley, depending on where your sewer source is. But again, different types of items. So when I built my addition, remember I was sharing that story? I got all kinds of cool things. I got access places all over the place. I got one behind a shower, so I get to my shower valve. My wife hates it. She said, that looks so ugly. I said, well, you know, I'll paint it so it matches the rest. She says, but I can still see it, right? She had to have this jacuzzi tub. Well, guess what I did with the jacuzzi? I got a breakaway in that jacuzzi so I can get to the pump if it ever leaks. I just take that, I unbolt it, and I push that entire, you know, enclosure out of the way, right, so I can get to the pump. She hates that too. She says, well, the model homes didn't have that. Well, yeah, the model homes don't maintain their own equipment either. So if I'm going to maintain it, I want to be able to get to it, right? Access ports to cables, you know, phones, and so on and so forth. So that's all. I mean, you can tell it's a facility manager's home. There's that stuff all over the place. Okay. Support equipment, power, and other related maintenance needs. Okay. Any other considerations? What else did we cover for the whole semester? What other type of maintenance considerations do we want to think about? Before we button that up and we leave the job site, what other maintenance considerations? I mean, you want to please a facility manager, right? Everybody nod yes, right? So you want to please a facility manager and says, gosh, this is such a great general contractor. Look at all this stuff that they gave me. So what's...
I would think in today's technology, you want to photograph everything.
Yeah.
Digitally,
okay.
And then you'll know exactly where it is.
Right. A whole suite. You know, when it tells you from the beginning to the end. Okay. And you're right. When you start construction, what is it to take a camera and start pictures of where, you know, where your cleanouts would be, as an example, but where your sweeps are for your power. Okay, where do the sweeps? Do they sweep to the right or do they sweep to the left? Okay, and whether they stub up. Okay, and not only that, but where's your access? Okay, where's your access vaults? Okay, those are going to be extremely useful. Documentation, O&amp information, spare parts, leftover parts for your pieces of equipment, going to be extremely well. Documentation, okay, such as installations. Valves in restrooms. Always install valves in restrooms for the sinks and separate them. Don't put one primary valve that shuts the entire bathroom down. You still have your main, but install secondary valves for all your lavatories. So I can turn off my sinks. So I want to change a caulk valve. I don't have to turn off all the commodes and all the urinals. Same thing with the toilets. I can have a separate valve for that particular one. And better yet, I have access that's labeled, right? Toilet shut-off valve, you know, behind access door. So you open it up, you go in and you turn off the valve, you perform the maintenance, you turn it back on, right? So again, efficient. I don't have to crawl up above the ceiling. My building was built in '54, so you can imagine some of the construction that we've come across. Some of it's scary. But again, you know, it's an older building, so you contend with it. Okay, so, but for many of you in this room, you're going to build new buildings ground up, right? So think about that. You know, before you turn it over to the facilities organization, is, you know, what would you like to see from a maintenance standpoint? Like I mentioned, you probably have them pass out on you when you mention that. It's like, where did you learn that? I didn't even know you knew maintainability, right? Okay, big items.